For centuries, humanity gazed at a familiar sky, populated solely by objects born within our solar system's embrace. Then, in a cosmic blink, the impossible happened. In 2017, Oumuamua shattered our expectations, an enigmatic object unlike any asteroid or comet we'd ever seen. 2 years later, Borisov, an icy wanderer trailing a familiar cometary tail, confirmed that we weren't alone. Now, defying all odds, the interstellar gates have opened again, revealing not one but two new visitors from beyond: 3I Atlas and SWAN R2. Think about this for a second. In the vast cosmic ocean that is our galaxy, a single solar system, our solar system, gets a visitor. That's rare. Then it happened again. What are the odds? It's like winning the lottery twice. But now, against all odds, it has happened again. It's mind-boggling! 3I Atlas appears to be larger and more intriguing than anything we've encountered before. Comet SWAN R2 is adding its own mysteries into the mix. Both are defying our expectations and breaking the rules of nature in ways that astronomers are struggling to explain. Now, let's be clear, the Milky Way is a sprawling metropolis of hundreds of billions of stars, each potentially surrounded by its own family of planets, comets, and drifting debris. But the distances between these stellar neighborhoods are so immense that even fragments ejected with tremendous force from distant systems can spend millions of years wandering the void, never encountering another sun. For most of human history, we believed our solar system was an isolated island, a lonely outpost in a black, endless ocean. The boundary marking the edge of our solar system, the heliopause, lies nearly 18 billion kilometers from the sun. It took the Voyager 1 probe over 36 years to cross that invisible frontier, traveling at speeds exceeding 17 kilometers per second. Even now, after nearly half a century, Voyager is only beginning its journey beyond the sun's protective bubble. The nearest star, Proxima Centauri, is more than 4 light-years away. That's a distance so vast that even light, the fastest thing in the universe, takes over 4 years to traverse it. Consider what it takes for a comet or asteroid to escape its home star's gravitational pull and make its way to us. It requires a cataclysmic ejection event, a perfectly aligned trajectory, and a head-on collision course with our relatively small slice of the galactic pie. Astronomers estimate that only a handful, maybe 1, 2, 3, interstellar objects large enough to be detected pass through the solar system each decade. This low number isn't because there are so few of them out there. Rather, it reflects the immense difficulty of finding them. Most of these interstellar wanderers are small, dark, and incredibly fast, hurtling through the inner solar system in a matter of days or weeks. They are often lost in the sun's glare or hidden among the crowded fields of distant stars. Even with a global network of telescopes, like Atlas in Hawaii and Chile, ZTF at Palomar, and Pan-STARRS in Maui, surveys can only capture a fraction of the sky at any given moment. Only the brightest and luckiest visitors have a chance of being recorded. The vast majority flash past unnoticed, their stories forever untold. Each detection, therefore, is a statistical miracle, a fleeting intersection of technology, precise timing, and pure cosmic randomness. The odds are astronomically stacked against us. Billions, perhaps trillions, of interstellar objects may roam the galaxy, but almost all remain hidden, too faint or too distant for even our most sensitive instruments. The discovery of just 3 interstellar interlopers, Oumuamua in 2017, Borisov in 2019, and now 3I Atlas, stands as a testament to both the enormity of the challenge and the unyielding curiosity of those dedicated to searching the skies. Every new arrival is a rare messenger, carrying secrets from a time and place far beyond our reach. The next interstellar visitor could pass through our solar system decades from now, or it might already be slipping past, unseen by any telescope at this very moment. With each confirmed crossing, the universe reminds us of how much remains unknown. In the face of such daunting odds, each detection is more than just a scientific achievement. It is a moment of contact with the wider galaxy, a fleeting glimpse into the mysteries that drift between the stars. Let's dive into the specifics of these cosmic travelers, starting with 3I Atlas. First off, size. Initial estimates placed its diameter somewhere between 5 and a whopping 19 kilometers. Think about that. That potentially makes it the largest interstellar object we've ever observed up close. Now, those are just estimates, mind you. The problem is that the nucleus, the actual core of the comet, is shrouded in a dense coma, a cloud of gas and dust that makes it tricky to get an accurate measurement. It's like trying to guess the size of a person hidden under a giant billowing blanket. Every attempt to model its brightness returns a range of possibilities, but all point to it being significantly larger than Oumuamua or Borisov. And then there's the color. Spectral data reveals a reddish hue, more so than any comet we've seen before. This redness is reminiscent of ancient, organic-rich bodies lurking at the fringes of our own solar system. The coma's polarization, the way its light scatters, suggests a mix of dark, carbon-rich grains and icy fragments, hinting at a long, cold journey through interstellar space. It's like the cosmic equivalent of a weathered traveler, carrying the marks of its epic voyage. But the chemistry, that's where things get really interesting. Early observations detected outgassing, the release of gases, at a distance far beyond where water ice typically vaporizes. Spectroscopy confirmed that this activity was driven not by water, but by carbon dioxide and carbon monoxide. In fact, the CO2 to water ratio was upside down compared to what we typically see in comets born in our own solar system. We're also seeing cyanide and even traces of nickel vapor in the mix, adding to the overall strangeness. What we ended up with is a comet that wakes up early, driven by volatile ices that somehow managed to survive being ejected from another star. Its activity is subdued but persistent as it races toward the inner solar system. Every detail, its size, its color, the chemistry of its coma, pushes against the boundaries of what we expect from a comet. It's almost like it's deliberately trying to defy categorization. But, and this is important, none of these traits, taken individually, actually break the laws of physics or chemistry. 3i Atlas exists in a liminal space, too large, too red, too volatile-rich to fit comfortably into any existing box, but not so alien as to be completely unexplainable. The real mystery isn't necessarily what it is, but how. It managed to survive the violence of ejection, the frigid temperatures of interstellar drift, and then the gauntlet of detection here in our solar system. Now, let's shift our focus to SWAN R2. This one was spotted by an amateur astronomer, Michael Mattiazzo, poring over data from the SOHO's SWAN instrument, which is designed to map hydrogen in the solar wind and often catches glimpses of comets as they approach the sun. At the time of discovery, it was already shining brightly, visible even through binoculars for those in the southern hemisphere. It also had a distinct straight, narrow tail stretching across the sky, suggesting strong activity for a comet that had just emerged from behind the sun. The timing of its appearance was actually quite clever. For over a month before discovery, SWAN R2 had been hiding in the sun's glare, an effect known as the helioshek effect, where geometry, not necessarily faintness, keeps a cosmic object hidden from view. As it swung past the sun, its brightness surged dramatically, leading to speculation about whether it was a single massive outburst or the slow unveiling of a nucleus packed with volatile ices. Professional observatories quickly jumped into action. The initial orbital calculations suggested a long-period orbit, perhaps thousands of years, with some models even hinting at an aphelion, its farthest point from the sun, stretching beyond 1,000 astronomical units. So, at the beginning, SWAN R2 straddled the line between being a first-time visitor from the Oort cloud and a rare returning wanderer. However, its behavior was anything but ordinary. The light curve, how its brightness changed over time, steepened as the comet moved away from the sun's glare, which is unusual. The coma glowed with a greenish hue, which is a telltale sign of diatomic carbon and cyanogen, while the tail maintained its sharp definition without breaking into streamers or fragments. All of this led to one conclusion. This was something out of the ordinary again. Now, before we move on, we have to address a rather unconventional hypothesis that popped up around 3i Atlas. In July of 2025, Avi Loeb, a Harvard astronomer known for stirring up controversy, published a paper suggesting that 3I Atlas might not be a natural object at all. He proposed that it could be a piece of alien technology, possibly even a probe with unknown intentions. Loeb based his argument on several key features. He pointed out that the object's orbital plane was suspiciously close to Earth's, suggesting it wasn't a mere coincidence. He highlighted its size, possibly over 20 kilometers across, which dwarfed previous interstellar objects, and he emphasized its speed and hyperbolic trajectory, guaranteeing it would never return. But what really caught his attention was the timing. Loeb noted that 3I Atlas would pass behind the Sun at perihelion, hidden from Earth-based telescopes during its brightest phase. He speculated that this could be a deliberate maneuver, a way to avoid observation, or even a chance to change course unseen. The paper was careful in its wording, but the implication was clear. Loeb referenced the dark forest hypothesis, the idea that advanced civilizations might send probes designed to stay hidden, acting only when shielded from prying eyes. He even suggested the object could be intentionally avoiding detailed observations or even deploying gadgets towards Earth from that hidden vantage point. As you might imagine, this hypothesis was met with a healthy dose of skepticism from the astronomical community. Many astronomers pointed out the likelihood of selection bias and the coincidental odds of such a small data set as the first 3 interstellar objects yielding a conclusion like this. Despite the criticism, Loeb's hypothesis did spark a debate. The object's orbit, timing, and sheer scale certainly left room for speculation. Loeb himself admitted that a natural explanation was most likely, but the idea had taken hold, blurring the line between scientific caution and the allure of the unknown. Why do these interstellar visitors matter? What's so significant about a rock or a ball of ice passing through our solar system? Well, the answer lies in what they can tell us about the vast unexplored territories beyond our own cosmic neighborhood. Each of these objects carries a story etched in its very fabric, a story of its origin, its journey through interstellar space, and the conditions it encountered along the way. It's like reading a message in a bottle that's drifted across an ocean, offering clues about a distant land. Imagine our solar system as a single house on a very, very long street. We know our house pretty well, its layout, its inhabitants, its quirks. But what about the other houses? Are they similar to ours? Are they made of the same materials? What kind of inhabitants do they have? These interstellar visitors are like postcards from those other houses, giving us a glimpse into their construction and environment, even though we can't physically visit them. By studying the composition of these objects, we can learn about the building blocks of planetary systems around other stars. Are they similar to the materials that formed our own planets, or are there significant differences? Are there elements and molecules that are rare or absent in our solar system but common elsewhere? The answers to these questions can help us understand the diversity of planetary formation and the prevalence of conditions that might be conducive to life. The trajectories of these interstellar objects also provide valuable information. Where did they come from? How long did they travel? What kind of gravitational forces did they encounter along the way? By tracing their paths, we can map the gravitational landscape of the galaxy and identify potential source stars or regions where these objects might have originated. It's like using a compass and a map to navigate through uncharted waters. But here's the catch: finding these interstellar visitors is incredibly difficult. As we mentioned earlier, the vastness of space and the limitations of our detection methods mean that we're only seeing a tiny fraction of the objects that are actually out there. Think of it like trying to find a single grain of sand on a beach that stretches for thousands of miles. Our current telescopes and surveys are like sieves with very large holes. They can only catch the brightest and largest objects, while the vast majority of smaller and fainter objects slip through unnoticed. This means that our sample of interstellar visitors is likely biased towards the most easily detectable objects, and we might be missing out on a whole population of smaller, more numerous objects that could be even more representative of the interstellar medium. The speed at which these objects travel also poses a challenge. Many of them are moving so fast that they only spend a short time within our solar system, giving us a limited window of opportunity to observe them. It's like trying to take a picture of a race car as it zooms past you. You need to be quick. And you need to have the right equipment. This is where citizen scientists come in. Just like Michael Matiasso's discovery of SWAN R2, amateur astronomers and space enthusiasts around the world can play a crucial role in the search for interstellar visitors. By analyzing publicly available data, monitoring telescope feeds, and sharing their observations, citizen scientists can help to identify potential candidates and alert the professional astronomy community to new discoveries. Their dedication and vigilance can supplement the efforts of professional surveys and observatories, increasing our chances of finding these elusive objects. It's like having thousands of extra pairs of eyes scanning the skies, increasing the probability of spotting something that might otherwise go unnoticed. But even with the combined efforts of professional and citizen scientists, there are still many unresolved mysteries surrounding interstellar objects. Where do they come from? What are they made of? What forces shape their evolution? These are questions that we're still grappling with. And the answers may require new technologies, new observing strategies, and new theoretical frameworks. The debate surrounding 3I Atlas and its potential artificial origin highlights the challenges of interpreting limited data and the importance of remaining open-minded, yet skeptical in the face of the unknown. While the scientific community largely agrees that 3I Atlas is likely a natural object, the mere suggestion of an artificial origin sparked a wave of interest and discussion, reminding us of the profound implications of discovering extraterrestrial technology. Ultimately, the search for interstellar visitors is not just about finding rocks and balls of ice. It's about pushing the boundaries of our knowledge, expanding our understanding of the universe, and exploring the possibilities of life beyond Earth. Each new discovery brings us one step closer to answering some of the most fundamental questions about our place in the cosmos. So, as we continue to scan the skies, let's remember that we're not just looking for objects. We're looking for clues, for stories, for connections to the wider galaxy. We're looking for a glimpse into the unknown, and who knows what we might find. The next interstellar visitor could be just around the corner, waiting to reveal its secrets and challenge our assumptions about the universe we inhabit. And that, my friends, is why these cosmic wanderers are so incredibly important.